The direction of motion of a motor vehicle is controlled by a steering system. A basic steering system has three main parts: a steering box connected to the steering wheel, the linkage connecting the steering box to the wheel assemblies at the front wheels, and front suspension parts to let the wheel assemblies pivot. When the driver turns the steering wheel, a shaft from the steering column turns a steering gear. The steering gear moves tie rods that connect to the front wheels. The tie rods move the front wheels to turn the vehicle right or left. There are two basic types of steering boxes: those with rack and pinion gearing and those with worm gearing. In both cases, the gearing in the steering box makes it easier for the driver to turn the steering wheel and hence the wheels. A rack and pinion steering system has a steering wheel, a main shaft, universal joints, and an intermediate shaft. When the steering is turned, movement is transferred by the shafts to the pinion. The pinion is meshed with the teeth of the rack, so pinion rotation moves the rack from side to side. This type of steering is used on passenger vehicles because it is light and direct. This steering system has worm gearing. It provides a gear reduction and a 90-degree change in direction. It has more parts and joints than the rack type, but it is more robust and may be used on heavier vehicles. To allow heavy transport vehicles to carry extra weight, two steering axles may be used. They're connected by a link to a common steering box. These vehicles are called tandem or twin-steered vehicles. Some passenger vehicles also steer the rear wheels slightly. This gives improved maneuverability. The system is known as four-wheel steering. It can be controlled mechanically through a direct connection between the front and rear steering boxes, or it can be computer-controlled. With heavier vehicles, increased use of front-wheel drive, and wider low-profile tires, more steering effort is needed, so power steering is used. An engine-driven hydraulic pump provides pressure that helps the driver steer the vehicle. The power steering system is designed so that the vehicle can still be controlled even if the engine or the power steering system fails. The steering system must provide control over the direction of travel of the vehicle, good maneuverability for parking the vehicle, smooth recovery from turns as the driver releases the steering wheel, and minimum transmission of road shocks from the road surface. The effort by the driver is transferred from the steering wheel down the steering column to a steering box. The steering box converts the rotary motion of the steering wheel to the linear motion needed to steer the vehicle. It also gives the driver a mechanical advantage. The linear motion from the steering box is then transferred by tie rods to the steering arms at the front wheels. The tie rods have ball joints that allow steering movement and movement of the suspension. The steering arm ball joints are arranged so that movement in the suspension does not affect steering operation.
Four-wheel steering can be computer-controlled or it can be mechanical through a direct connection between the front and rear steering boxes, or the rear wheels can be mounted on special compliant mounts. As cornering forces are applied to them, they alter the steering angles. In all cases, the amount of steering available at the rear wheels is limited by the manufacturer. In each type, there is an emphasis on increased maneuverability and/or stability of the vehicle under different driving conditions. In mechanical systems, there is a direct link between the front and rear steering racks through a center steering shaft that allows the rear wheels to be steered within prescribed limits. In hydraulic and electric assisted systems, the center shaft is replaced either by hydraulic lines or by electrical connections that are controlled by control valves or computer-monitored sensors. The relationships between the steering system, the wheel positions, and the suspension system form what is called the steering geometry. These relationships must always stay within manufacturer specifications. With heavier vehicles, increased use of front-wheel drive and wider low-profile tires, more steering effort is needed, so power assistance is commonly used. A hydraulic pump is driven from the engine to provide pressure to help the driver. The power steering system is designed so that even if the engine or the power steering system fails, the vehicle can still be controlled. However, much more driver effort is required.
The rack and pinion steering gearbox has a pinion connected to the steering column. This pinion runs in mesh with a rack that is connected to the steering tie rods. This gives more direct operation. Both the pinion and the rack teeth are helical gears. Helical gearing gives smoother and quieter operation for the driver. Turning the steering wheel rotates the pinion and moves the rack from side to side. Ball joints at the end of the rack locate the tie rods and allow movement in the steering and suspension. Mechanical advantage is gained by the reduction ratio. The value of this ratio depends on the size of the pinion. A small pinion gives light steering, but it requires many turns of the steering wheel to travel from lock to lock. A large pinion means the number of turns of the steering column is reduced, but the steering is heavier to turn. Ratios vary, depending on the type of vehicle. But in each case, the ratio is the same for all positions of the wheels. It is a fixed ratio.
A disadvantage of a fixed ratio system is that towards the lock positions, more effort is needed by the driver. This is because the angle of the steering arms reduces their effective length, and that reduces the leverage on the wheels. To overcome this, many rack and pinion systems use variable ratio steering. The ratio is made variable by changing the shape of the teeth on the rack between the center and the outer edges of the rack. Then, as the steering moves away from the straight ahead position, the ratio, and therefore the mechanical advantage, increases progressively. As the pinion turns and moves on the rack, the gear contact point between the pinion and the teeth on the rack changes. This change in tooth contact changes the effective diameter of the pinion. Then, for the same amount of steering wheel rotation, the rack moves a shorter distance near the ends of the rack than near the center. Effort needed to turn the wheel stays approximately the same through the whole range of movement.
The steering rack is supported at the pinion end by being sandwiched between the pinion and a spring-loaded rack guide yoke. This spring-loaded yoke ensures free play is eliminated between the gears, while still allowing for relative movement. The rack is supported at the other end of the rack housing or tube by a bush, normally of nylon. Nylon is used because it has a low coefficient of friction and low wear rate. The pinion is supported by two bearings in the rack housing. These bearings are preloaded to keep the pinion in the correct position, relative to the rack, and to eliminate free play. The rack and pinion steering box is normally lubricated by grease. Each end of the rack is protected from dirt and water by a flexible synthetic rubber bellows, attached to the rack housing and to the tie rod. The bellows extends and collapses as the tie rods move away from and towards the housing as the rack moves. On some vehicles, both bellows are interconnected by a tube, so that as the steering wheel is moved from side to side, air is transferred from the collapsing bellows side to the expanding bellows side. Rack and pinion type steering gears are used because their construction makes them compact and lightweight. Their steering response is very sharp because the rack operates directly on the steering knuckle, and there is very little sliding and rotation resistance, which gives lighter operation.
A worm gear has teeth cut in the shape of a helix. The steering box is a gearbox. It converts the rotary motion of the steering wheel to the linear motion needed to control the wheels. Its gear ratio increases output torque and reduces the effort the driver has to apply. The input, attached to the steering column, is called a worm shaft. It is meshed with a sector or portion of a gear mounted on its own shaft at right angles to the worm. The outer end of the sector shaft has a tapered spline which mates with an internal spline on the pitman or drop arm. As the steering wheel rotates, the worm shaft causes the sector to move through an arc and transfer the motion through the pitman arm to the steering linkage. Variations to this principle include the worm and roller and the worm and nut. The recirculating ball steering box is a popular development of the worm and nut and worm and sector principle. Both ends of the worm shaft are supported in the housing by angular bearings, which are preloaded to reduce end float and side thrust movements of the worm when it's under load. A ball nut rides on the worm, supported on the spiral grooves of the worm and on the inside of the nut by many balls. The balls form a low-friction internal thread, which causes the nut to move up or down on the worm as it rotates. With rotation, the balls are rolled along the grooves, partly in the worm and partly in the nut, and they circulate by passing through ball return guides at each end of the nut. External teeth on one side of the nut mesh with the teeth of the sector gear formed on the sector shaft or pitman shaft, and this transfers the motion through the pitman arm to the steering linkage. The sector gear and nut teeth are designed so that when the teeth are in the straight ahead position, they have minimum clearance. This reduces free play in that position. The pitman shaft is supported by two caged needle roller bearings in the steering box housing. The sector teeth are angled, and an adjustment screw on the steering housing cover provides proper engagement of the sector gear and nut teeth. The worm shaft in a worm and roller steering box is supported in a similar manner to the recirculating ball type, but the worm has an hourglass shape, and it meshes with a double-track roller mounted on bearings on a pin attached to the pitman shaft. As the worm rotates, the roller moves in an arc, following the hourglass shape and transferring the motion to the pitman shaft. The hourglass shape changes the steering ratio slightly as the steering wheel is turned from the central position towards each lock.
Increased applications of front-wheel drive and wider low-profile tires places additional loads on front wheels. Steering then demands more effort from the driver. Power steering helps to reduce the additional effort needed. It's of most benefit during slow cornering and when parking. Assistance is provided as soon as the steering wheel is rotated in either direction, and it's designed so that even if system failure occurs, the vehicle can still be steered. An engine-driven hydraulic pump delivers hydraulic fluid to the power unit at the steering box, or rack and pinion, through connecting hoses and pipes. The fluid reservoir can be mounted on the pump, or it can be separate. With the engine running, fluid flows continuously from the power steering pump to the steering gear and back to the pump. With the steering wheel in the neutral position, little pressure is needed to maintain fluid flow, and little engine power is needed to operate the system. When the steering is turned, a rotary valve integral to the steering input shaft directs fluid to one side or the other of a piston attached to the steering gear. Pressure then increases as required to provide assistance. In a worm and roller steering box, the piston slides in a cylinder in the casing. It has an extension formed on one side with teeth which engage teeth on the pitman shaft. Pressure applied to either side of the piston produces a force, which is transferred through the teeth to help turn the pitman shaft. In a rack and pinion steering gear, the piston is formed centrally on the steering rack, and the rack housing provides the working cylinder. Seals at each end of the cylinder isolate the power section from the rack and the helical pinion. Seals in the rotary valve section at the pinion input prevent fluid leakage there. Connecting pipes transfer fluid from the rotary valve housing to one side of the piston or the other to provide assistance, which acts directly on the rack. The rotary valve is located between the steering gear input shaft and the pinion gear. It consists of an inner member, which forms part of the input shaft, and a surrounding sleeve member fixed to the pinion gear. Turning the steering wheel makes both members rotate in the steering gear housing, but it is the slight relative rotary displacement of the inner member and the sleeve member which controls and directs the power steering fluid flow. This slight rotary displacement is allowed by a torsion bar, which is connected to the pinion gear at its bottom end and the input shaft at its top end. When the steering wheel is turned, there is resistance from the front wheels at the road surface. This resistance is transmitted through the rack to the pinion gear so that the input shaft twists slightly on the torsion bar. Since the inner member is also attached to the input shaft, this twisting provides a relative rotary displacement of the inner and outer members. It is this displacement that lets fluid flow through the valve to act on the piston at the steering gear. The input shaft can twist through only a small angle before it contacts a stop on the pinion gear. This is needed to provide manual steering when power assistance is not available. With the engine running and the steering in the neutral position, fluid flow is directed into the valve assembly through drilled holes in the outer sleeve. As soon as the steering is turned to the left or right, the slight relative movement occurs between the inner and outer members. In the neutral position, the inner member lets fluid pass equally to both sides of the rack piston and return to the fluid reservoir. Equal pressure is applied to both sides of the rack piston. No power assistance is needed. When the steering is turned, fluid is restricted from making a free return to the reservoir. It is now directed to the side that matches the turning action. At the same time, fluid on the opposite side is directed to the return circuit, back to the reservoir. Slight rotation of the valve gives a small amount of assistance, which becomes progressively greater as the torsion bar flexes, and more assistance is needed. The grooves of the inner member are precisely shaped to meter the flow of fluid. All power steering pumps have a flow control valve to vary fluid flow and power steering system pressures. A pressure relief valve prevents excessive pressures developing when the steering is on full lock and held against its stops. The flow control valve is located at the outlet fitting of the pump. During slow cornering or when parking, pump speeds are normally low. There is less demand for fluid flow, but to provide the required assistance, high pressure is needed. Discharge ports direct the fluid to the outlet and then to the steering gear. The outlet fluid pressure is slightly lower than the internal high pressure coming from the pump. This drop in pressure occurs as the fluid flow passes the needle and orifice in the outlet fitting. This lower pressure is transmitted through a bypass fluid passage to the spring end of the control valve. The pressure difference on the valve causes it to move away from the outlet fitting, but the force of the spring prevents it moving far enough to uncover a return port back to the pump inlet. Movement of the control valve controls the position of the needle valve in the outlet fitting, and this controls the fluid flow to the steering gear. At higher speeds with no steering maneuvers, fluid flow is increased. This reduces pressure at the outlet. The lower pressure is transmitted to the spring end of the control valve. The valve moves and opens the return port back to the pump inlet. Movement of the control valve also controls the movement of the flow control needle in the outlet fitting. The needle closes in the orifice, and fluid flow to the steering gear reduces. With the steering wheel held at full lock, the steering rack power piston chamber becomes fully pressurized, and fluid flow stops. This high pressure is transmitted back to the spring end of the control valve, opening the pressure relief valve. A small amount of fluid passes through the pressure relief orifice, providing a pressure drop. The valve moves and uncovers the return port to the pump inlet. A predetermined relief pressure is thus maintained. The pump is normally a vane type, with sufficient capacity for all operating conditions.
Effort applied to the steering wheel is transferred down the steering column or shaft to a steering box. In early cars, the steering column was a straight shaft running inside a hollow tube. The steering wheel was attached to one end and the steering box to the other. In many frontal collisions, however, this caused serious injury to the driver, partly because it was forced back towards the driver's head and partly because the sudden stop forced the driver onto the wheel. To reduce this hazard, some steering columns are fitted with collapsible sections that protect the driver. During a collision, two forces are applied to the steering column. The first is the force of the steering box being forced back towards the steering column and towards the driver. Plastic shear pins allow the lower shaft to move over the upper shaft. The second force is the mass of the driver striking the steering wheel. This force breaks the brackets on the upper part of the column, driving the upper column into the lower column. The steering column is connected to the input shaft of the steering gear by a flexible joint. This allows for alignment and reduces the transmission of road shocks back to the driver. Some steering columns have an intermediate shaft, which runs at an oblique angle from the column to the steering gear. In a collision, the universal joints on the shaft allow it to fold under, preventing the force from impact being transferred directly to the column. Some manufacturers fit sensors and control units to the steering column, which provide information to steering control modules as part of an electric-assisted or four-wheel steering system. The sensor and control units are able to sense rotational pressure exerted by the driver and control both the speed and direction of the electric motor. This motor is contained inside the steering rack and provides the steering assistance. The steering column may also include switches for lights, indicators, wipers, and an ignition switch and lock assembly.
The major components of the suspension system must be firmly located to withstand the forces that occur in normal operation. Control arms fasten a component like a rear axle assembly to the vehicle body, while allowing it to move as it needs to. Similarly with a steering knuckle. The arms must be strong enough to withstand the forces due to normal operation, but light enough to minimize the vehicle's unsprung mass. The front suspension can have one or two control arms. Parallel link front suspensions have two control arms. Vehicles with strut-type front suspension have only one arm. It can be a wishbone shape with two fulcrum mounting points or straight with single fulcrum. The inner end of the control arm is bushed to the vehicle body, and the outer end uses a ball joint to allow changes in the steering angle for turning. This rear-wheel drive vehicle has coil springs in the rear suspension. Therefore, special provision must be made to locate the axle, laterally and longitudinally. Trailing arms or control rods are used to position the axle longitudinally. They have flexible rubber mountings at each end where they locate on the axle housing and on the chassis frame. They would allow the axle to move laterally if it were not restrained. Any such movement has to be controlled to keep correct alignment with the front wheels, and the vehicle frame. This suspension system uses angled upper control rods to limit lateral movement of the rear axle during cornering. They also absorb the torque reaction forces, which limits rear axle windup during accelerating and braking. A panhard rod may be used to restrict lateral movement of the rear axle during cornering. It has bushes or mountings at each end, where it locates on the axle and frame. This allows for variations in load while maintaining correct alignment. The axle may also be located by a Watts linkage. A lever, mounted on a pivot near the center of the axle housing, is connected by rods to the frame on each side of the vehicle. This maintains the axle in alignment with the frame, while still allowing the suspension to move vertically. The steering linkage is a combination of rods and arms that transmit the movement of the steering gear to the front wheels. It must transmit this movement to the front wheels, while still allowing for up and down movement they may make, while the vehicle is in motion. The type of steering mechanism and the number of linkages depends on the type of steering box, its location, and the type of suspension on the vehicle. Passenger cars with independent suspension and using a worm-type steering box may have the steering box mounted so that the linkage is in front or behind the suspension crossmember. When the linkage is behind, it is protected by the crossmember from possible damage, and the position of the steering box reduces the length of the steering column. Steering wheel movement is relayed through the steering gear and pitman arm to a center track rod. The center track rod is connected to the pitman arm at one end and to a steering idler arm at the other end. The idler arm assembly is bolted to the vehicle frame, and the idler arm is positioned parallel to the pitman arm. It can then relay the steering box movement accurately to the opposite side. A tie rod on each side of the vehicle connects each wheel assembly with the center track rod. Flexible joints on the track rod and on the ends of the tie rods allow for steering and suspension movement.
In forward control vehicles, the steering system is mounted in front of the engine and wheels. The steering box is mounted on the subframe with the pitman arm vertical. A drag link transfers movement of the pitman arm to a relay lever which has two arms, one connected to the drag link and the other to the idler by the track rod. The longitudinal movement of the drag link pivots the relay lever. This transfers the motion through the track rod to the idler arm and through the tie rods to the wheels. In four-wheel drive vehicles with a beam axle, the single track rod connects the steering arms on each wheel assembly across the vehicle. In this design, the drag link is connected to an arm on the front of the left-hand wheel assembly. Movement of the pitman arm is transferred through the drag link to the left-hand wheel and through the track rod to the right-hand wheel. The steering box is offset from the steering column, so two universal joints and an intermediate steering shaft are used. Off-road vehicles of this type without power assistance often use a steering damper. It resembles a shock absorber and operates on a similar principle. It's mounted between the track rod and either the rigid axle or the vehicle frame. When the vehicle is driven over rough terrain, its purpose is to prevent shocks being transmitted through the steering linkage and back to the steering wheel. With rack and pinion steering, the linkage is simpler, since the rack itself is part of the linkage. Movement of the steering wheel is transferred through the steering column, intermediate shaft, and universal joints to rotate the pinion, which moves the rack from side to side. A tie rod with a ball swivel at each end of the rack relays the movement directly to the steering lever on each wheel assembly. The rack can thus be considered as the centre track rod of a three-piece track rod system. The steering lever or steering arm is linked to the tie rod or track rod by a flexible ball joint that allows for suspension movement and steering rotation. The lever, the stub axle, and the stub axle carrier can be forged as one piece and can be referred to as a knuckle. They can also be made as separate units and assembled to form one piece. Each steering system makes provision for adjustment of the linkage to achieve the manufacturer's recommended toe setting. The track rods or tie rod ends are threaded to provide for their lengthening or shortening.
Bushings act as bearings at suspension fulcrum points to allow for movement of the component while maintaining its alignment. They can be metallic or made of rubber, nylon, or urethane. In commercial vehicles, metallic bushings are commonly used as shackle bushings for leaf springs. Any force applied to the bushing acts through it to the body of the vehicle, which results in a harsher ride. The mounting pin on a metallic bushing is usually drilled to allow for lubrication. Rubber bushings isolate noise and harshness, and dampen unwanted vibrations. Rubber bonded bushings can be used to mount the steering rack to the vehicle frame. The rubber absorbs small impacts from the suspension action, without transmitting them to the vehicle. Rubber requires no lubrication. Spring shackle bushings can be molded to form two halves, to fit into each side of the spring eye on the swinging shackle. With the spring loaded and the shackle plates tightened, the rubber is compressed in the eye and at the face of the plates. As the spring deflects, the rubber shears without tearing. Metalastic or rubber bonded bushings are normally used for the front eye of the spring at the fixed shackle point, and also in control arm applications. The bushing has a steel outer casing and inner sleeve. The rubber medium is bonded to both to provide flexibility between them. The outer casing is normally pressed into place in the component. Relative movement between the casing and the inner sleeve causes the rubber to shear without tearing. In control arm applications, particularly at the rear of a vehicle, the rubber bushing may be molded with a voided section. This is known as a compliance bushing because it allows the unit or component to comply with a controlled amount of movement in the direction of the void. This movement relative to the vehicle frame allows compliance or deflection steer of the road wheels when cornering. Since this influences the steering behavior of the vehicle, it is very important that the voided section is in its correct relative position. Ball joints are swivel connections mounted in the outer ends of the front control arms and on the steering track rods and tie rods. They allow the control arms to move up and down with suspension deflection and also let the wheel and hub assembly turn for steering. The ball joint can be a sealed, self-contained unit fastened to the control arm in a number of ways. It is made up of a pressed steel housing, fitted with sintered iron seats and a hardened ball stud. A taper on the stud locates in a mating taper on the suspension unit, and a rubber seal keeps out dirt and water. Some ball joints can be dismantled to replace the seats and ball stud and allow for adjustments. Shims between the upper and lower halves of the joint allow free play to be controlled. Grease nipples can allow for periodic lubrication, but most joints today are sealed for life, and no regular maintenance is required. On tie rod ends, the ball joint is usually self-contained and attached to the tie rod by internal or external threads.